Disc Lecture 5D, Tuning and Troubleshooting Work Queue Programs. By now, you should have created at least one work queue program and run through the example with several workers. Now you'll find as you scale up, you're likely to run into problems sooner or later simply because a distributed system is a very dynamic environment in which many things can go wrong. So in this lecture, I'm going to give you some tips and techniques for tuning and troubleshooting work queue programs as you scale them up. This includes running multiple tasks per worker by specifying resource needs explicitly, discovering task resources when you don't know them already, logging and plotting master statistics and performance, and turning on debug output to diagnose technical problems. So first, let's talk about running multiple tasks per worker. If you really want to scale up to a large number of tasks, you want to be able to run as many tasks as you can on a worker. If that worker has 64 cores, it'd be nice to be able to run 64 one-core tasks. But that won't happen automatically. Unless you tell it otherwise, work queue will assume that any task can run on any worker and that one task occupies a whole worker. Now this is a safety measure because we don't know up front just how many cores that a given task is going to use. But work queue can do a better job if you tell it two things. One is to specify the number of cores, memory and disk and other resources, that each task needs. And the other is to enable automatic resource detection on the worker. Let me give you an example. Suppose I have a master that wants to run a variety of tasks. Some of them consume 1 core, some of them consume 4 cores. Now by default, if I just start a single worker without any special options, that worker will implicitly only run one task at a time that consumes 1 core. Right? So the best that's going to happen here is that 1 core is going to run on that worker, and that's it. Now if we want more things to run simultaneously, what we have to do is start a worker. And we can manually set how many cores, memory, and disk it has, but the easiest thing to do is simply set it up automatically by specifying -- cores auto. In this case, let's suppose that worker discovers that the local machine has 4 cores. So it's going to advertise that fact to the master. And now it's going to be able to run any combination of tasks up to a sum of 4 cores. So it could either run that single large 4-core task by itself, run it to completion, or it could run 4 single-core tasks simultaneously until they complete individually. Now, it's much better to have a single worker managing a large number of tasks than it is to have a large number of workers on the same machine, simply because those tasks can share a cache directory, and so files needed by those tasks can be uploaded to the worker one at a time. You're going to have a much more scalable system. Now, to make this work, you have to tell work queue how many cores and other resources are needed by each task. And if you know this, you can specify it automatically. Using C or Perl, you state work queue task specify cores, the number of cores. Same thing for memory and disk. And there's a simpler syntax if you use Python. Now, if you know that, you can put it in, and work queue will do the best job it can for you. But sometimes you don't know those things up front, and you need a way to discover them automatically. So we provide a tool called the Resource Monitor, shown here as RM. And the Resource Monitor is a wrapper around an existing application, which will run it to completion, and then produce a little JSON record that tells you all of the resources consumed by this task. So in this case, mysim.exe ran for 183 seconds of wall time, consumed 176 seconds of CPU time, used 4 cores, 8 processes, 49 megabytes of memory, and 1,309 gigabytes of disk. Turns out the Resource Monitor measures well over 100 things, so that record is quite large and detailed. So if you don't know what resources each task uses, you can use the Resource Monitor to figure that out. Now, a handy trick is within a work queue master program, you can turn on automatic monitoring. And what happens here is as each task runs, work queue will automatically turn on the Resource Monitor to measure the resources consumed by that task. And then as the task is returned, work queue uses that information as an assumption of the resources needed by other tasks. So once you turn on automatic monitoring, work queue will automatically size each task to the resources that it thinks it needs. By the way, you can also do the same thing in Makeflow by turning on the -- monitor option, and you'll get a record dropped in the monitor directory for every task that is run. Now, it is also helpful when things aren't going as expected to turn on some performance logs. So you can do this by stating work queue specify log and the name of a log file. And then the master will periodically write into that log file a record that indicates how many tasks are running, waiting, completed, how many workers are connected, and a variety of other figures. And you can look at that manually if you want, but it's easier to just plot it by using the tool workQGraphLog. And this will produce a graph like this. So on the x-axis, we have the runtime of a complete application that took almost 100 minutes. On the y-axis, we have the number of tasks running, waiting, the number of workers busy, and the number of cores currently in use. There are a lot of other things that you can plot if you want. In this particular example, we see that the number of tasks waiting oscillates between 6,000 and 12,000. This is because the particular application keeps generating new tasks in batches. And that the number of cores in use slowly climbs up to about 1,500 and then ramps off as the tasks finish. Now, if things aren't going as expected, I have one important piece of advice, which is to go back to the simplest case that you can and make sure that works before you try scaling up again. That simplest case is to run one master program with one worker and make sure that works. If that isn't working, there's no point in running multiple workers. Then the second bit is to turn on debugging in the worker, because this will reveal a lot of detailed information about what's going on inside the machine. So let me give you an example. This is a case of giving a bad project name to a worker. By turning on debugging, we can figure out what's going on. So here, by turning on the debug log, we can step through each line one at a time, and we can see that first the worker examines its sandbox directory and sets it up. And then it goes to query the catalog for available masters. It makes an HTTP connection to the catalog. The connection is okay, it gets some results back, and then it disconnects. And then you see here on the very last line, it says project name my project matches 0 masters. So the worker went to the catalog, asked about a particular project name, and nothing matched. Now in this case, the worker will sit and wait for a while and try again, wait for a while and try again, but if nothing ever shows up, it's going to wait forever. So the problem here is that either we gave the wrong project name to the worker, or the wrong project name to the master, or possibly the master hasn't been started yet. But that gives you an idea of where to start looking for a problem. Here's another common problem, which is that a firewall blocks a connection. This often crops up in institutional clusters that have a lot of network controls in place. So here again, we're running workQWorker, we turn on dall, and we see that the sandbox gets set up, and then it looks up the name master somewhere.edu. It gets an IP address, and it tries to connect to the IP address. And then there's a long wait, and we see that the connection failed. Now, this long wait followed by a failure almost always indicates a firewall that is preventing any sort of connection at all. If there was no firewall, but there was also no master on the other side, usually we'd get that failure rather quickly. So a long wait usually means a firewall, and you're going to have to talk to your system administrators or network operators to figure out why traffic is being blocked. Right, so I hope that gives you some idea for solving problems with WorkQ. You're going to encounter strange things. Distributed systems have unusual failure modes. So make use of tools like performance logs and resource reports and debug output to get details and figure them out. And whenever you have problems, I strongly recommend that you go back to the basic case. Try setting up one master and one worker and get that working. When it's going, then scale up to 10, and then to 100, and then to 1,000 to make sure that you've got things working before you start consuming a lot of resources. All right, that's my advice. Go out and build large applications with WorkQ. Good luck.